Thank you.
Yeah. Okay, it's 5:30, so let's get started today. So welcome everybody. So we are continuing our online lectures, or virtual lectures. I guess that's what they want us to say. So the difference between this one and last week is that obviously I'm in my home right now. So because of the executive order given by the governor, they don't want even the faculty to be on campus. So they I visited there a couple of times earlier this week, and they had some police there kind of patrolling. So they're really trying to enforce people to stay from home. So you can look into my personal life a little bit. This is my apartment, and we'll continue from here. Okay. So before we get started today, there was a couple questions on the homework, or one question that I wanted to kind of address together, and then after that, I wanted to make sure that we, if the other people had questions, we can answer them too. Okay. But first, let me tackle Jeff's question. So the question Jeff asked was on problem 3B on the homework. So 3B was a 2D unsteady problem. Okay. Oh, first of all, can everyone hear me okay? The audio's fine and everything? I'm going to assume that's...
Yeah.
Yeah, okay.
Yeah, sounds good.
Okay, and you can see my, you can see that I'm writing on my iPad right here, right?
Yep.
Yes.
Got it. Okay. Okay, so in problem 3B on the homework, I asked you to write the code for a 2D problem. In particular, I wanted you to do it for an implicit Euler. Okay. So in particular, the question that was asked was, how do we handle the Neyman conditions, right? So in this problem, we had 3 Neyman conditions. So let me draw out the domain. So our domain looked like this. So we had a square just like normal, right? At the top of the domain, we had d phi dn is equal to 150 cosine of 4 pi t. Right? On the right side, we have a no flux boundary condition. So we have d phi dn is equal to 0. And then on the bottom side, we have d phi dn is equal to 150 sine of 4 pi t. Okay. And then on the left side, we have a Dirichlet condition, which, I won't go over that just because, we kind of do that. So the question is, how do we handle these Neyman conditions here? Right? Okay. So just like we did before, these Neyman conditions will turn into an algebraic equation. So let's do just the bottom one, just so you can kind of see. So let me clear the screen. So on the bottom, we had d phi dn is equal to 150 sine of 4 pi t. Okay. And so just like we always do with these Neyman conditions, we're going to take this derivative here and then approximate with finite differences. Okay. So we're going to say phi at the inner minus phi at the boundary all over delta y in this case, since it's on the bottom face. And this is going to be equal to 150 sine of 4 pi t. Okay. So here we can see we're almost at the equation, but since we're doing an unsteady problem, we need to assign these a time index. And so for implicit Euler, remember what we do is we assign everything to the n plus 1. Okay. So let's go ahead and do that. So we say n plus 1, n plus 1. Okay. So then if we move this delta y over to the other side, what we get is phi inner at the n plus 1 minus phi boundary at the n plus 1 is equal to 150 delta y sine 4 pi t. Okay. And so this equation right here, this turns into the algebraic equation that you can put into your matrix. Okay. So basically, for every boundary node, okay. Okay. So for every node that sits on the bottom boundary, you're going to apply this equation right here. Right? So then you get an algebraic equation where on the right side you have a 150 delta y sine 4 pi t. So this quantity right here, when you're applying this in MATLAB, this will go into your right-hand side vector, which we usually call b in the code. Okay. And then these right here, these are your coefficients for the left-hand side matrix. Okay. All right, so you do it kind of exactly the same as before. It's just the only tricky thing is that you have to add these time indices. And so what you choose for those time indices depend on, whether you're doing explicit or implicit Euler. Okay. Does that make sense, Jeff? That clear things up a little bit?
Yeah, sorry. Thank you.
Okay, sounds good. Okay, so are there any other questions on the homework before we move on with the lesson today? Okay. So hopefully the homework was okay for you guys. Did you guys enjoy the starter codes? Just because I know there's kind of been a lot of moving around in the last few. I know it's been must have been really hectic for you guys. So I thought I'd give you the starter code to kind of help you guys out with that. So hopefully that was useful. Right? So if there's no more questions, let's go ahead and move on. Okay. So let's continue where we left off last Wednesday. So last Wednesday, remember what we were doing was diffusion problems in using finite volumes. Okay. So just a quick refresher, since it's been it's been a week since we've seen this. We were starting with 1D problems. So in 1D, our diffusion equation looks like this. We have minus k d dx of d phi dx is equal to q of x. Okay. And so what we do in the finite volume method, which is different from finite difference, is that what we're going to do is we're going to integrate this over the length of a cell. Okay. So in one dimension, or in 1D, our mesh looks something like this. Okay. So we have a line, and then we have grid points. Okay. So when I say that we integrate it over the length of the cell, what we're doing is we're taking, a cell like this, and we're integrating from the left side to the right side. Where we call the left node, we'll call that XL, and then the right node, we'll call that XR. Okay. So let's go ahead and do that. So we have integral from XL to XR of minus k d dx of d phi dx is equal to integral from XL to XR q of x dx. Okay. And then so what we need to do is we need to take this equation and we're going to form an algebraic equation from this. Okay. And remember the way that we do that is we apply two integration tricks, I guess what we like to call, in order to turn this integral equation to an algebraic one. So this will become more clear when we do 2D. But the tricks that we do is we use the divergence theorem. And so what the divergence theorem lets us do is it lets us turn the integral on the left-hand side, which is an integral over the entire length of the cell, or in 2D, it'll be over the entire area of the cell, and convert that into quantities that we can evaluate just at the boundaries. Okay. So for 1D, it's the divergence theorem is just simply just doing the integral, but you'll see kind of the power of the divergence theorem once we do 2D problems. Okay. And then the other integration rule that we use is the trapezoidal rule. And remember, the trapezoidal rule lets us evaluate integrals, without actually performing integration, by basically evaluating the integrand at the centroid of the cell. Okay. And so the details for that were in the lecture last time, so I'm just kind of skip to the result, but I kind of just wanted to just kind of jog your memory into how we got here. Right? So are there any questions on just the kind of the review from last week? Okay, so I'm going to clear the board. Okay. So once we did all that, we did all those integration rules, we ended up with the following equation, right? So we got phi at R minus 2 phi at C plus phi at L is equal to minus delta x squared over 2 times q at xc. Okay? And so the way that we're going to apply this equation, right, is we're going to take our grid, right, our grid which is filled with all these cells. Okay? So in this case, I have seven cells. Okay? And then what we're going to do is we're going to apply this equation to every single one. Okay? And so, what these different symbols mean, let's go over it quickly. So phi r, this is the neighbor on the right. Phi c, this is my own value. And phi l, this is the neighbor on the left.
Professor, what do you mean by your own value?
So that's when we applied finite differences to each grid point, that was kind of the phi value at that grid point. So let's say if we apply this to cell number 2, phi c would be phi 2 in that case.
Makes sense. Okay.
Mm-hmm. Right. So actually, let's do that. So actually, let's apply this to node number 2 or cell number 2, just so we can see how this is. Okay. Okay. So for cell 2, the right neighbor is going to be 3. So we have phi 3 minus 2. Phi c is my own value, so that's going to be phi 2, right? Plus the neighbor that's on the left, phi l, so that's going to be phi 1. Okay? And that's going to be minus delta x squared all over 2 over times q times x, q of xc. Okay? Oh, sorry, that's not 2. This should be k, our diffusion coefficient. Sorry about that. I think I was looking at an example where that is actually 2, but it's more generally that should be k, or diffusion coefficient. Okay. Right. So then now that we have this equation here, we can form our algebraic equation for all the interior nodes. Okay. Okay. So all those nodes 2, 3, 4, 5, 6, since they're on the interior, those are taken care of. Okay. So what we don't know yet is how do we handle these nodes here on the boundary, or the cells on the boundary, sorry. Okay. Because we know that on the boundary, these cells are going to be affected by the boundary conditions, so we need to account for these when we do the equation. Okay. And so what's going to be different in finite volumes, kind of as we talked about before, is that when we apply the boundary conditions on these cells, they don't actually become the equations, but what they do is that the boundary conditions will modify these equations. Okay. So this probably represents the biggest difference in between what we did for finite differences and what we're going to be doing for finite volumes, is that you can't just look at a boundary condition here and just apply in a formula there. You need to see how that boundary condition kind of modifies your base case, where your base case is given by this equation up here. Okay? So some people like finite volumes better because you know that you're always going to be working with the same equation. You're just going to make modifications to it. But then some people think making the modifications is a little bit complicated, so they'd rather just deal with the boundary conditions just straight up. So, in the end, it's going to be a matter of personal preference. But we'll see kind of both cases, and you can kind of decide which one you think is a bit better. Okay. Any questions on this before I wipe the board? Okay. Okay, so let's start going into boundary conditions. Okay. So just like before, we have both Dirichlet and Neyman conditions. So let's go over both. So let's start with Dirichlet. Remember, Dirichlet boundary conditions are when we prescribe the value directly. Okay. So if we do an example here, so let's draw a line. Okay. So let's say that on the left side right here, we have a prescribed value of phi naught. Okay. And so let's use that value. Okay. So if we go back to where we performed the integration for our finite volume formula, we got the following case. Okay. So we have minus k multiplied by d phi dx evaluated xr minus d phi dx evaluated xl. Okay. And this is all equal to qc times delta x. Okay. So this was kind of a few steps down after we performed the integration. So this was basically right after we applied the divergence theorem on our equations. Okay. So we haven't yet applied the trapezoidal rule, or we did on the right. And oh, actually, yeah, this is after we applied the trapezoidal rule. So we had already done the divergence theorem and the trapezoidal rule. Okay. Okay. So remember, at this point, what we did before was that we took each of these derivatives here, okay, and then what we did was we approximated them using finite differences. Okay, so let's do the same thing here, but let's take the prescribed boundary into account. Okay. So let's do the right side first. So actually, since the prescribed value here is on the left, okay. Our right side will stay the same. Okay. So for our right side derivative, we have phi at r minus phi c long over delta x. Okay. So that's the finite difference representation of that derivative at that interface. Okay. So now let's approximate the derivative on the left side. Where on the left side here we have this phi naught. Okay. And just to remind you, the phi c that we're talking about is right there, and the phi r is right here, right? Because remember, these phi values they don't exist at the nodes anymore. What they do is they exist at the self centers, okay? Where this distance is delta x. So if we want to approximate the derivative on the right-hand side, we can use the values that are available to us. The values that are available are going to be phi c, or on the left-hand side, sorry, phi c and phi naught, which is our prescribed boundary. And then what we need to do in order to account for the fact that this distance is shorter here is to divide by not delta x, but delta x over 2. Okay? Okay. And the right-hand side still stays the same. So on the right-hand side, we still have q of xc times delta x. Okay? So since the Dirichlet boundary condition, that phi naught is a lot closer to phi c than phi r, we have to divide by a different distance. Okay? So this, this distance right here is shorter because distance to Dirichlet boundary is shorter. Okay. So let's go ahead and simplify this equation a bit. Okay. So let's multiply both sides by delta x like we did and divide by k, right? And so what we get for a Dirichlet boundary condition is BR minus 3 PC, right, plus 2 times phi naught is equal to minus delta x squared over k times q at xc. Okay. It's a little messy here. Let me box it a bit for you. Okay, so we basically all I did there was I just basically simplified it so that I can get the coefficients. Okay, but there's something that's interesting here. Okay. So normally this is where we would stop if we were at an interior node, but we're not at an interior node. Okay, so in particular, I want to draw your attention to this term right here. Okay. So this term is 2 times phi naught, where phi naught is our prescribed value. And so what's unique about this term is that we know everything about it. Okay, so phi c and phi r. So those terms we don't know. So those are going to be in the left-hand side. But since we know what phi naught is, what we can do is we can move this. Oops, that's not what I wanted. We can move this to the right-hand side since it's known. Okay. So we can actually write this in a little bit of a better form. That we can apply for both our code and kind of for our hand calculations. Before I do that, are there any questions on this board before I wipe it?
Yeah, Professor, can you write down where the second cell would be at? So the center phi is between phi naught and node 1, I believe.
Right. Yeah. Yeah. Let me do that. Okay.
I'm sorry, I just wondering.
So I'll highlight in blue right here. So the node that we're integrating over is right. Or the cell that we're integrating over is this one right here, right? So that's where phi c is, and then the only cell or the only neighboring cell is going to be on the right, and that's going to be this one right here. Okay.
So phi right is you're talking about the entire cell, not the nodes anymore.
Right. Yeah. So phi right in this case, that's the center. That's the value of phi at the center of the right cell. Yeah. So it's kind of the value for that kind of encapsulates the entire cell.
Okay. Okay. Got it.
Yeah, it's a little bit of a paradigm shift from what we did before. Because before, you know, we always worried about the nodes, but for finite volumes, what we're worried about here are the cells. Yeah, so it takes a bit to kind of you know, change that mindset, but it's you know, that's something to kind of always keep in mind when we're doing finite volumes. Yeah. Okay. Any other questions on this board before I wipe it? Okay. Sorry, my clear button was obscured. Okay, so we can write the final form of the Dirichlet boundary condition. Okay, so we have phi r minus 3 phi c is equal to minus delta x squared all over k times q at xc minus 2 phi naught. And so this right here, this is the finite volume equation for 1D diffusion. for a Dirichlet boundary condition on the left. It's a little bit long. Okay. So you can see, it was a little bit different from how we normally arrive at these boundary conditions, but the form is the same, right? So on the left-hand side of this equation, we have everything that's still kind of unknown. So we have everything in terms of phi r and phi c. So we haven't solved those yet, so we won't solve those until we actually, solve our linear system of equations. Right? Versus everything on the right here, which is our forcing function or our source term, q, and our Dirichlet boundary phi naught. So everything over here is known. Okay, so then, so the unknown side, this will become our left-hand side matrix. And then the known side, this will become our right-hand side vector. Okay. So we'll see how this turns into code kind of in a little bit with the example that I've done. Okay, so that's the Dirichlet boundary condition. So actually, if you remember from finite differences, when we had Dirichlet boundary conditions, those were kind of the easier ones to apply because we just directly supplied the value. When we do finite volumes, it's a little bit flipped. So in finite volumes, Dirichlet boundary conditions are a little bit more inconvenient to apply just because you have to do kind of the half width. You got to move the thing over to the right. So Neyman conditions are actually a little bit simpler. So let me kind of show you what that means. Right. So let's do now Neyman conditions. Okay. So let me draw our line again. Okay. So remember, Neyman conditions are conditions where we supply the derivative. Okay. So in a 1D case, what we can say is that on this right boundary, we can set a Neyman condition of gamma. So we say that d phi dx at that right boundary is going to be equal to gamma. So let me label our cells. So here we have our cell of interest. So this will be phi c. And on right here, this will be our left neighbor. So this will be phi l. Let me draw this a little bit better. C. It's really hard to do curve stuff on the iPad. Okay, so let's find out the finite volume equation for a Neyman condition. Okay, so basically kind of the Neyman version of kind of what we have at the top for Dirichlet. Okay? So let's start at the same place. So let's start at our finite volume equation after we've applied the divergence theorem and after we applied the trapezoidal rule. Right? And so that equation looks like this. Okay, so we have minus k times our diffusion terms, which is the d phi dx evaluated at the right side of our cell. Okay, so here's our cell. Minus d phi dx evaluated at the left side of the cell, right, is equal to our source term times delta x. Okay, okay, so now let's apply the Neyman condition. So the Neyman condition says that d phi dx at the right side of the boundary is equal to gamma. So fortunately, just because of the way that we've formed these equations, we actually already have that directly in here, right? So if we look at this term right here, right? This term right here is saying that this is, what we need to plug in here is d phi dx at the right side of our cell. So luckily for us, we know exactly what that is due to the Neyman condition. So d phi dx at the right side of the cell is just going to be gamma. And so what we're going to do is we're going to just put gamma in this equation, right? So we don't have to do any finite differences. We just kind of just throw that in, and then we'll be good to go. But this guy, this will kind of be kind of the same as before. So we will have a little bit of finite differences just from the left side, but you know, on the right side, we're kind of safe from that. So the Neyman conditions here are a little bit more convenient. Okay. So any questions on this before I wipe the board? Okay. Okay, so let's go see how we do that. So if we replace that that derivative on the left-hand side with gamma, what we get is minus k times gamma, and then we replace that one with the finite difference. So this can be phi c minus phi l, all divided by delta x. This is equal to q at xc times delta x. Where this right here, this is known. Okay. So let's do the same thing that we did before with the Dirichlet condition, where we move, we put everything that we know on the left-hand side, and then everything that we everything that we don't know on the left, and then everything that we know on the right. Okay. So we do that, we get the following. So we get minus phi c plus phi l is equal to minus delta x squared all over k times qc plus gamma delta x. Okay. And so this equation right here, this is the FVM equation. For 1D diffusion. And a Neyman condition on the right. Okay. Okay. So now we can do Dirichlet conditions, we can do Neyman conditions, and we can do interior cells. So so we have everything that we need. So the next thing is we're going to do an example just to see how it all kind of puts together. So we'll do the example first by hand, just so you can see how the equations come up, and then I'll show you how that's implemented in MATLAB. Okay. So any last questions before we jump into an example? Okay, so let's jump right in. Okay, so in this example we have the following equation. Right. So in this example we have 3 times d squared phi dx squared is equal to 2x squared. Okay. Where the boundary conditions, we have the following. So we have a Neyman condition on the left. So we have d phi dx at x is equal to 0. This is equal to 0. So we have a no flux boundary condition there. And on the right, we have phi at 1. This is going to be equal to 10. Okay. And so at first, let's do this, just on a small grid, just so we can do it by hand. So let's do it on a grid of 4 cells. Okay. Okay. 1, 2, 3, 4. And just so just so we can evaluate Q, our source term, let's write out the coordinates for the cell centers. That was weird. Okay, so we have x1. The center of the cell is going to be 0.125. x2, this is going to be 0.375. x3, this is going to be 0.625. And x4, this is going to be 0.875. Okay, because the length of the domain is going to be 1. Okay, so the distance from here to here is 1, and that means delta x, since we have 4 cells, can be 0.25. Okay. All right, any questions on just the setup? All right. And one more piece of information. Let's identify k. So we can see here that k is going to be -3. Okay. So k is -3 because normally there's a minus in our equation, as you can see, kind of from up here. Okay. So since we have a +3, that means k must be -3 in order for that to be positive. Okay, so let's set up these equations using finite volumes. Okay, so first let's start with the interior node, since we have an equation that can do that. Okay. So in the interior nodes, where our equation looks like this, so we have phi r minus 2 phi c plus phi l is equal to minus delta x squared all over k. Made the same mistake again. Q at xc. Okay. So we have two interior nodes in this case. So our interior nodes are going to be node 2 and node 3. Okay. So let's write out the equations for that. So for node 2, we have to first do our right neighbor. So our right neighbor is going to be phi 3 minus 2 phi c. So phi c is ourselves. Okay. So that's going to be phi 2. Plus phi L, which is our left neighbor, so that's going to be phi 1, right? And this is going to be equal to delta x squared, so that's going to be 0.25 squared all over k. So k in this case is -3, so that minus is minus going to cancel out, so we have -3.
Professor, how come the diffusion coefficient k is negative or the opposite sign?
Right. So in our normal diffusion equation, it looks like this. So we have minus k d squared phi dx squared is equal to q. Right. So in this case, we just had 3 d squared phi dx squared. Right. So because we had a +3 in the problem, that means k must be -3 in order to cancel out kind of this negative that's right here.
Okay, that helps out.
Yeah.
Thank you.
Mm-hmm. Okay, so that's equation 2. So now let's do equation 3. Okay. So equation 3, we're going to apply the same formula, except everything kind of gets shifted to the right. So let's do phi r. So phi r is our right neighbor. So our right neighbor for cell 3 is going to be cell 4. So we have phi 4 minus 2 times our self, which is phi 3, plus our left neighbor, which is 2. Okay. And on the right-hand side, we have mostly the same 3. Okay. But instead of 2x2 squared, we have 2x3 squared because we're on the right side. Okay. And so these are 2 of our equations here. Okay. So since we have 4 cells, we need 2 more equations, and we're going to get those 2 equations from the boundary conditions. Okay. Okay. So are there any questions on these interior nodes here, or interior cells? Okay, so let's do the 2 boundary conditions. So let's start with the one on the left. So on the left here we have a Neyman condition. So it's actually it's a little bit different than the equations we did before. Because before, if you remember, the equation that we derived was for a Dirichlet on the left, Neyman on the right. So for this example, I thought I'd switch it up just to kind of show you kind of how you would do it in that case. So let's go back to our first equation. Okay. So after we applied the divergence theorem and we applied our trapezoidal rule, we get the following. Okay. So we have minus k times d phi dx evaluated x r minus d phi dx evaluated xl. Okay. This is equal to q at xc delta x. Okay. So when we were doing the Neyman condition before, what we did was we replaced this this derivative right here with our Neyman condition. Okay, but in this case, our Neyman condition is not on the right; it's on the left, right? Because what our boundary value problem told us was that d phi dx at x is equal to 0 was equal to 0. Okay, and so what that means is that we're going to take instead, we're going to replace this guy with that. Because if you go back to kind of the problem statement, we saw that the Neyman condition with d phi dx at x is equal to 0 is equal to 0. Okay. So in this case, it's actually really simple since it's just equal to 0. So if this is equal to 0, then this gets crossed out completely. Okay. And so let's replace this first term right here with a finite difference. Okay. So if we move k over to the left-hand side, we get phi r minus phi c all over delta x is equal to minus delta x all over k times q at xc. Okay. And then if we apply this for node number 1, this will give us the equation for cell number 1. Sorry. Okay. Any questions on this before I wipe the board? Okay, so if we apply this for cell number 1, we get the following equation. Okay, so phi r in this case will be phi 2 minus phi c, which is 1 in this case. Okay, and then we plug in the values for delta x, and then for k, and we get 2x1 squared. So that takes care of our Neyman condition on the left. So now let's do our Dirichlet condition on the right.
Professor, for this class, for finite volume method, are we going to assume that Neyman conditions are going to be 0? And if they're not 0, I'm just wondering what the problem would look like if that entire term wasn't 0. Or for this class, we're going to assume that one term will most likely be 0.
Yeah. So so in general, you can't always assume that that's going to be 0. So let me actually write out just that equation again. Okay. So in the last problem, we took this term and we said that is equal to 0 because that was the condition. But what if we had instead something like this? So where d phi dx at x equals 0 is equal to 7. Okay. So instead of crossing out this term, what we're going to do is we can just replace this with the condition. Okay. So in the last part, we replaced it with 0 because it was a 0, so it just canceled it all out. But if we had this was equal to 7, we would replace this with a 7. Right? So in order to apply Neyman conditions, you just look for the derivative that you're going to replace, and then just replace it with the appropriate value that they give you from the problem.
Okay, sounds good. Thank you.
Yep. Okay, so let's do the Dirichlet condition on the right. So the Dirichlet condition on the right was given by this. So we said that phi at 1 is equal to 10. Okay, so this will give us the equation for cell 4. Okay. So let's go back to this equation right here. It's kind of convenient that I wrote this. Okay. And then now, since we have our Dirichlet condition on the right, let's replace this term right here. Okay. Because since we know the value on the right-hand side, that's going to change how we compute this derivative here. Okay. So let's do before. So let's replace this with a finite difference. Okay. So this is going to be phi 0 minus phi, in this case 4, right? Since we're doing this for cell 4, right? Okay. So let me draw why that is. Okay. Okay. So we know that phi 0 is equal to 10. Okay. For cell number 4 right here. Okay. So when we compute the derivative at the right side of the cell, we need to take that 10 into account, right? So the way we do that is we do phi naught, which is our Dirichlet condition, minus phi 4 divided by delta x over 2, right? So that's going to be the derivative on the right side of the cell, minus the derivative on the left side, which is going to be phi 4 minus phi 3 all over delta x. Okay. And this is equal to q delta x q at xc. Okay. And so in order to get our last algebraic equation, all we need to do is simplify this. Okay. And we can simplify this by taking this phi 0, since we know what this is. Right. So we can just plug in 10 for that, because that's what the Dirichlet condition basically specified. Okay. Okay. Any questions on this board before I wipe it? Okay, so let's wipe the board. Okay. Okay, so finally, if we do that and we plug everything in, we get 20. Where this guy is 2 times phi 0, okay, minus 3 phi 4 plus phi 3 is equal to minus 0.25 squared all over 3 minus 3 times 2x4 squared. Okay. And so since this is known, let's move this over to the right-hand side. So in the end, we get minus phi 4 plus phi 3 is equal to 0.25 squared all over 3, 2x 4 squared minus 20. Okay. And this right here is our fourth equation. Okay. So we started with a diffusion equation on 4 different cells. So we needed 4 algebraic equations. And so we've done that. Okay. So we did 2 equations based on the interior cells. That was kind of the first thing we did. That was cell 2 and cell 3. Then we did the equation for cell 1, which is the Neyman condition. And then finally, this is the equation for cell 4, which is the Dirichlet condition. Okay. So 4 cells, 4 equations. So then we know that we're good to go. Okay.
That's not 20, right? It's 2 phi naught.
Yeah, 20 is 2 phi naught. Correct. All right. Any last questions on this before we jump into the MATLAB code? Okay. So let me share my computer screen. Okay. All right. So what you see, actually, let me maximize this. It's a little bit bigger. Zoom in. View. Let's see. Okay. So I'll figure out how to zoom in another time, because it's a little bit hard to read. But I'll kind of explain things kind of line by line. But can everyone kind of read the code okay that on their screen? Or is it's a little bit hard, huh? Because it's a little bit small. Okay. So let me kind of just go through line by line, and we'll just kind of talk about what each line means. Okay. Okay, so let's start at the top of the code here. So the structure of the code is same as before. So I usually like to write my codes in kind of the same format. So hopefully it's you guys are getting used to it now. So in section 1 of my codes, I always like to define all of the problem parameters, all the parameters for the problem. Okay. So let's go through kind of some of the more important ones that we'll use. Okay. So let's start with this line 7 right here. Okay. So in line 7, I have n is equal to 4. Okay. So this was this was in all of our finite difference codes. So we always had an n value. But what I wanted to highlight here was that n represents something different. So instead of representing the number of grid points in our mesh, what this represents instead is the number of cells, right? Because remember, in finite volumes, we're worried mostly about the cells, not on the grid points. Okay. Okay. So the next things I want to highlight are these two lines. Okay. So first we have line 8. So line 8 is the same as before. So line 8, this will give us the position coordinates for all the endpoints. So those will be for all the grid points in our mesh. Okay, so that's still the same. But for finite volumes, remember what we need instead are the cell centers. Okay, so I've created this new vector xc. So xc, what this tells us is the location for all the cell centers. Okay, so this will be really important for when we're applying our source term. Okay, because for the source term we need the coordinates at the centers, not at the endpoints of our grid. All right. Okay, and then you can see here I've set the diffusion coefficient. So I've set it just equal to +3 because I've kind of canceled out the negative there. Okay, so those are just the problem parameters. So that's pretty straightforward. Besides the fact that we're counting the cells instead of the grid points, that should be the same. So where I want to kind of focus most of the attention here is on section 2, which is this for loop I have right here. Okay. So let's start kind of at the top. So at the top right here, you see that we're looping. We do a loop. So every time that we write this code, we always write it in terms of loops, just so we visit every single cell. And I'll put cell in all caps. Right? So I have a loop index I cell, and that's going from 1 to n. So this will let us visit every single cell in our mesh. Okay? And so what I've done here, and this is kind of trademark for a lot of the finite volume codes, because remember for finite volumes, you're instead of writing a whole new equation for the boundary conditions, what we're doing instead is we're modifying it. So one thing that I like, or one way that I like to implement this is I like to use an if statement. Okay? So let's go over the first if statement here. So if I cell is equal to 1, so we have the very first cell in our mesh, so this is cell 1. So what this means is that we're on the left side. And so what that means is we need to apply our Neyman boundary condition. Okay? So if we go back to our equations, we know that the coefficient for myself, or phi underscore c, is going to be -1. So that's what I've done here. So I said that the coefficient at I cell, comma I cell, so this is the diagonal term, is equal to -1. Okay? And then I have the coefficient for the right neighbor. Okay, so this is a at I cell, comma I cell plus 1. So in this case, this is 1, comma 2. So this is the coefficient for the right neighbor here. So this can be equal to 1, just like we said in our equations. Okay? And then on the right-hand side here, we have just the source term. So on the source term, we have dx squared divided by 2, or dx squared divided by k times 2 times the xc at I cell squared. Okay, because remember our source term here was 2 times x squared. And then since we don't have a Neyman condition, or since the Neyman condition was 0, then this terminates here. But usually, if you do have something like the Neyman condition was 7, then you would add that 7 kind of at the end of this line right here. Okay, so that's for the left side. So now let's do the right side. So on the right side, we have our Dirichlet boundary. So once again, you see I'm setting the coefficients. So for the Dirichlet boundary, we know that the coefficient for our diagonal term is going to be -3. Okay? And then the coefficient for our left neighbor is going to be 1. So that's what I have right here. Okay? And then for the right-hand side, we have our source term. So this is still the same as up there. Right? And then to account for the Dirichlet boundary, I've subtracted 20 from this equation. Okay? All right. And then finally, we have the else statement. So the else is going to be, remember, that's going to be the catch-all. So if we're not at the left boundary or we're not at the right boundary, then the only other place that we can be is on the interior. Okay, so that's what this says right here. So else, we are on an interior cell. So here we apply our interior equation. So where the coefficient for myself, or the cell in question, is going to be -2. And then you put a coefficient of 1 for both the right and the left neighbors. And then our right-hand side vector is going to be this expression right here. Okay? So same as before. Right? So this for loop is going to visit every cell. So depending on what index of the for loop, we're going to enter into a different entry into this if statement. So every time we loop, we just choose 1. Right? And then once we're out of this for loop, then our matrix and vectors are complete. And so once we do that, we're ready to solve. Okay, so then that's what I do right there. Okay. And so let me run this for you just to kind of show you. Okay, and for this particular problem, I didn't compute it in the notes, but I computed the exact solution. Okay, just so you can compare. So in the plot that just showed up here, I have the finite volume solution in blue, and then I have the exact solution in red. Okay, so you can see that they're very close. And then as we increase the number of cells, so let's add a 0 here. So let's make this 40. So we know that as we refine our grid, then our solution will get more accurate. Okay. So we run the simulation, and you can see that we reach really good accuracy. So you can't see it, but there are 2 curves in here. So there's one basically right on top of the other. Okay, so that's the MATLAB code, right? So that's uploaded on Titanium. So so you can definitely download this code and peruse it. And if you want to kind of cross-reference to the recorded lecture, because I'm gonna throw this up on YouTube after it's done, you can kind of see kind of my thought process for kind of each section and kind of each line of this code. Okay. Okay. Are there any last questions on 1D diffusion that I can cover here? While I'm bringing up this the notes again. All right. If there's no questions, so then let's move on to 2D diffusion. Okay. So definitely, we don't have enough time today because it's already almost 6:30 to finish this. So we'll probably pick this up after the spring break, because next week is spring break, so we're not going to have any class next week. But since if you guys are working on the project next week, I'll still have my normal office hours next week. So I'll do the Zoom meetings for that. So if you lost the links for the Zoom links for the office hours, they're on the Titanium under announcements. But I'll move those links over to the kind of the top section, so they'll kind of be readily available to you, kind of just like we talked about at the beginning. Okay? So next week, spring break, so we'll have no class, but I'll have my normal office hours. So if you want to chat during those times, then I'll make myself available. Okay?
Professor, I had a quick question. Do you know any status on, I believe, the next midterm and the final, and how that will be taken? Or is that like a thing that the school university has been kind of discussing?
Yeah, so the basically what the university says that they're under no circumstances are we allowed back on campus. So that means that any exams that we have to do will be online. Okay. So in this class we have one more midterm exam, right? And we have a final project. So for the final project, there's nothing that we need to be in class for. But for the midterm exam, I'm going to make that a take-home midterm. So I'm going to post the midterm exam basically at 5:30 p.m. On the day that we would normally take it, which I think is like April 17th or 18th or something like that. And then you'll have 24 hours to basically finish that and kind of upload the PDF onto Titanium. Okay? So that's basically how I'm going to do that. Right?
Okay. Will that I don't know if this is a weird question, but does that will you increase the difficulty, or you make it just as it would be, or you know what I mean, because take home?
Yeah, that's you normally for a take home exam you would make the the exam difficulty more a little bit higher to kind of compensate for that. You know, just because it's, you know, first of all, you have a lot more time to do it, and you know, it's, you know, I can tell you guys not to use like your notes or, you know, the YouTube lectures or anything like that, but there's no way I can police that. So, you know, of course people are going to use that. But for this class, you know, it's this class is so unique in that, like, I used the midterms before to kind of test you on kind of the theory and kind of developing the equations, and kind of once you get kind of the recipe down, then they're all kind of the same as that. So it's, unless I kind of introduce MATLAB into the midterms, which, you know, I'm kind of undecided at this point if I want to do that, then it's going to be kind of pretty similar to the first midterm, because it's, you know, once you kind of get the recipe on how to, you know, get these equations, algebraic equations using finite volumes, then they're all more or less kind of the same way. So right now I don't know, so I might put MATLAB stuff on the midterm. I think that would be, you know, that could be something that we could do, because, you know, you'll be doing it at home and you'll have MATLAB on you. But I'm still kind of undecided on that, because my original plan was to have the midterms kind of test you on the theory, and then the final project will be my way to assess, you know, how well you can implement this in MATLAB. So I'll kind of have more I'll have more news for that kind of after spring break, kind of after I think about it a bit more.
Okay, sounds good. I appreciate it. Thank you.
Yeah. Okay, so let's do 2D finite volumes. Okay. So we just did 1D problems, so we kind of did it in kind of very excruciating detail. So let's do the same thing for 2D. Okay. So our starting point will be our diffusion equation, but in this time it's going to be in 2D, right? So in 2D, I'm going to use the vector notation. So our equation is going to look like this. So we have minus k times delta del times the gradient of phi. Okay. Right, and that's going to be equal to qxy, right? Where since now that we're in 2D, our source term can be a function of x and y. Okay? And so just like we did in 1D, let's take this equation and let's integrate it. Not from, over the length of a cell. Okay, so let's go ahead and do that. So we have minus k times the double integral a okay. So we have this this term now. Okay. So just like we did in the 1D problems, we're going to use our integration rules in order to do this. Okay. So the first step is going to use the divergence theorem. Okay. Because what we want to do is we want to convert this integral, instead of an integral over an area, to an integral over the boundaries. Okay. So when we apply divergence theorem in 2D, what that does is it transforms our double integral into a line integral. So let's go ahead and do that. Right. So instead of a double integral on the left, we have a line integral on the right. Okay. Where I've used this notation, kind of dA, to basically say that this is on the boundary of A. Okay. Right. And then in the integrand, we have the gradient of phi dot n. Okay. And since this is a line integral, we're going to do ds. Okay. And then times the double integral of qxy. Okay. Okay. And so now that we're at this point, we can use our trapezoidal rule. Okay. To basically evaluate this integrals. But before we do that, I kind of want to talk about this integral on the left. Okay. Because a lot of the finite volume methods in 2D, they kind of really depend on how we do this integral. Okay? Okay, any questions on this before we I wipe the board? Okay, so let's go ahead and wipe the board. Okay, so let's look at that that integral there. Okay, in particular, let me draw a two-dimensional cell. Okay, because in 2D, what we're doing is a you know, basically a square. Okay? And so what's unique about that line integral is that we're only doing it around the boundary. Okay? So what I'm going to do is, since we have this square, I'm going to label each of the boundaries by basically compass directions. Okay? So the top boundary, I'm going to give it the symbol M for north. The right boundary is going to be E for east. The bottom boundary is going to be S for south. And the left boundary is going to be W for west. Okay. Okay, and then let me draw in some dimensions. So let's say that the vertical length of this cell is going to be delta y, and the horizontal length is going to be delta x. Okay. All right. And so since we have this this cell like this, when we do a line integral around the entire boundary, okay. So basically, we want to go around this entire thing right here. Since we have kind of 4 distinct faces, we can break up that line integral into kind of 4 distinct parts. Okay? So let me show you what I mean by that. So, so we kind of starting with this integral right here. So we have minus k times line integral around the entire boundary of the gradient of phi dot n hat. Okay, where n hat right here, let me kind of write that in. N hat here is our kind of our outward unit normal. Okay, so that's a vector. Okay, so we're going to take the dot product of those 2 vectors, which we'll do in a second. Okay? But for this case, is what we can say is that instead of kind of going around this whole thing, what we can do is we can break this into 4 integrals. Okay, so let's go ahead and do that. So let's start with the east integral. Okay, so there's going to be integral. So I'm not going to put a circle around this because, you know, it's that circle, what that represents is kind of a full rotation. Since this is just going to be the integral on just the east side, you know, it's not going to be a full rotation. So instead, I'm going to give it an integral sub e for east. Okay. Okay. So the integral on the east face of the gradient of phi dot n ds. Okay, and then we have the same thing for all the other ones. Okay, so next we have the integral on the north face plus integral on the west face plus integral on the south face. And so what this allows us to do is it allows us to basically basically evaluate each of these integrals because you know, because each of the sides of the square are flat, doing each of these integrals here is going to be a lot simpler. Okay? And then this is also multiplied by delta minus k. Okay? So can't forget that. Okay. All right. Any questions on this before I wipe the board? Okay.
Professor, was it all of it multiplied by negative k?
Yeah, all of it was multiplied by negative k.
Thank
Okay. Okay. So now that we've broken up that integral into 4 different parts, let's pay attention to the integrand. Okay. So I've just kind of been writing the integrand out, right, without kind of really explaining it. But actually, let's actually go through each one. Okay. So first, let's go through you know, what the gradient of phi is. Okay. So remember that whenever you take the gradient of a scalar like this, it turns into a vector. Okay. Okay. So in particular, that vector looks like this. So we have a d phi dx comma d phi dy. Okay. So that's our delta phi. And then this n right here, this is the outward unit normal. And so what that is basically is that for each of the faces on our square, right, what we have is we need basically a vector on each side that basically tells us which side is out. Okay? And so that basically what the outward unit normal is. Okay? So depending on which side of the square that we're on, n hat is going to look different. Okay? So let's write out what the n hats are for each side. Right? Right? So we have north, south, east, and west. So on the east side, our n hat is going to the right. So if you do that in component form, it looks like this. So our n hat is going to be 1, 0. Okay? On the north side, our normal vector is pointing up. So it's going to be 0, 1. So on the west side, our normal vector is pointing left. So that's going to be -1, 0. Okay? And on the south side, our normal vector is pointing down. So it's going to be 0, -1. Okay. Okay. So keeping in mind that our gradient of phi, it looks like this. Okay. And we're doing a dot product between this this delta with all of the with all these normal vectors here. This basically simplifies our the evaluation of each integral. Okay. And so let me kind of write down what each of those are, and that'll kind of probably be the last thing that we do today. Okay. Okay. So let's take the east one first. Okay. So on the east side, we have this. Okay. So on the east side, we have the gradient of phi dot product with n. Okay. Okay. So let's actually write out what all those are. So the gradient of phi is given by d phi dx, comma d phi dy. Okay. And then let's take the dot product with the normal vector on the east side, which is this guy. Okay. So 1, 0 ds. Okay. So when you take the dot product, you basically multiply the matching components and then add them up. Okay. So we're going to take d phi dx, multiply by 1, and then we're going to take d phi dy and then multiply by 0 and then add them up. Okay. And so what this says is that this is going to be equal to d phi dx ds. Okay. So by performing that dot product, that actually kind of simplifies it so that we know that at the east face, we only need to evaluate basically d phi dx. So we don't need to worry about d phi dy at all. Okay. Okay, so let me write out the expressions for all the other faces, and I think we'll probably call it there today. Okay, so let's do the north face. Right? So north, we have same things. We have the gradient of phi, so that's d phi dx, comma d phi dy, dot product with the normal vector there, so it's going to be 0, 1 ds. Okay, and so if we do that, this gives us, we do these multiplication. So we have d phi dx multiplied by 0, so that's going to go away. So we get d phi dy ds. Okay. Okay. So now let's do the west face. So on the west face, our normal vector is -1, 0. Okay. So what this is going to give us is minus integral of d phi dx ds. Okay. And then finally, let's do the south face. which looks like that, okay? So we basically, we've taken the normal vectors and we've taken the gradients and we use that to evaluate these integrals, okay? And so what we'll do after the spring break is we're gonna add all these guys together, okay? And then use the trapezoidal rule to evaluate them at the faces, and we'll use that to get our algebraic equation for 2D diffusion, okay? Okay, so we're out of time for today, so let's wrap it up here. So just like I did for the last week's lectures, I'm going to this is recording on my computer right now, so I'm going to throw that up on YouTube, and that'll be available to you probably either sometime later tonight or tomorrow morning. Okay. So have a great spring break, everyone. Hopefully, stay safe and stay healthy. If you can, make sure you stay home. Don't go out unless you can really need it, because it's really tough times. And I will see you guys in a little bit over a week, I guess. Okay. So I'll see you guys then. All right, have a great break, everybody. And for those of you wondering, yes, I saw the messages from Dwayne "The Rock" Johnson, but when those happen, you shouldn't acknowledge that. Otherwise, the trolls will. You can't feed the trolls when they do stuff like that. All right, so I'll stay on the line for a little bit. I have another lecture at 7, but if you have any further questions, you can ask me for the next probably 5-10 minutes. Thanks, Rick. You too. Okay, I'm going to sign off.